This is Daniel Coosbury, and in this video we're going to move past just looking at normal probabilities and look at a really special theorem that's going to allow us to apply our knowledge about the normal distribution to some stuff we've done way back when with the sample mean in particular. So let's start with the definition of a sampling distribution. So here's a picture of a population of things. So just picture just a big box, the big box I like to draw with just the population. And imagine we want to know things about the population, and we take a sample, and we can find the mean of that sample like really, really nicely. And let's just say we're trying to find, I don't know, what's the population mean? We don't really know, but we can take a sample, and we can find a sample mean of just that sample. Now imagine going back to that population and taking a completely different sample. So here's another one. And it's a completely different one. Maybe there's overlap, maybe there's not. And I can find that sample mean all the same. And I can keep doing this, frankly, as much as I want. And the idea is if we do this a lot, we can end up with a bunch of different sample means from the same population. So see how these are all being drawn from the same population. Well, it turns out if you were to do this enough times, your sample means would follow their own special probability distribution. So these things are going to be random. Which is a really interesting property of the sample mean. These are random, which means they have a probability distribution. So if you take a random sample, all of these things that you sample are random. The mean's going to be random. And here you do another one. This is random. This is random. So it turns out the sample mean is random, and it has a distribution. And so we're going to call the distribution of X bar a sampling distribution. That kind of comes from the idea that you got to take a bunch of samples to get a distribution for X bar. But the thing kind of take away from this slide is just like when you sample a bunch of things and they're all random, this is finding the mean of those things is also a random thing. And so we could take a bunch of different samples, and those means would be all random, and they would have their own special distribution. So this is kind of a nice thing to write down. And X bar is a random variable because they're all random. You go into a population, you take a random sample. You can't tell me what the sample mean is going to be until you take the sample and find it, because it's a random thing. So it's also the distributions of sample means called the sampling distribution. So what I want to show you is it's called the central limit theorem, and we're applying it in this video to X bar. And so what the central limit theorem does is it tells us under certain conditions, the distribution of the sample mean is going to be really, really nice. And we're going to be able to work with it. Okay, so let me read this to you. Let X bar be the mean of a normally distributed or a large, simple random sample from a population with mean, sigma, and standard deviation. I'm sorry, mean, mu, and standard deviation, sigma. In other words, let's assume that we either have a normal population. This is probably a better way to write it. Normal population, meaning we know the population is normal. For instance, like we know like SAT scores are normal. So in that population, you take a sample, you know you're getting normal things. Or you just take a large sample, whether it's normal or not, this is going to work for a large sample. So we've got this condition or that. This is the math or, which means this one, that one, or both. It could be both. It's fine. But you only need one of these to be true. And we know the population mean, and we know the population standard deviation. And so we're assuming we know those things. Then X bar has approximately normal distribution with the mean of X bar equal to mu and the standard deviation of X bar equal to sigma over n. That's kind of covered up right there. So in other words, we're saying that X bar, the sample mean, is a random variable, which means it has its own special distribution. And under these conditions up here, that distribution it's normal. So that's important. It's normal. With mean equal to mu, the population mean, and sigma equal to sigma over, the standard deviation equal to sigma over the square root of n, where that's the sample size, that's the population thing. So this is called the central limit theorem. This whole thing's called the central limit theorem. I've kind of written in a different way just to show you how useful this is going to be. If the data is normally distributed, or if n is greater than 30, so a large sample, then X bar, the sample mean, is going to be normal with the mean mu and the standard deviation sigma over n. So this is different than just taking one thing, because this is our standard deviation now, sigma over square root of n. So we'll call this mu with a little x bar down here. We'll call this sigma with a little x bar down here. It's this number right here. You got to take these two things, divide them, do the square root thing, and you'll get your thing. So this is really, really powerful. So the way we're going to use the central limit theorem is we're going to check and make sure one of these conditions is true. And if it's true, that means we can find probabilities for x bar using this thing right here, which I think is going to be really, really nice. So let me just give you one big example like in some other videos, and we'll find a bunch of different probabilities. So here we have Hereford cattle are one of the most popular breeds of cattle. Based on data from the Cattle Society, the mean weight of a 1-year-old bull is 1,135 pounds with a standard deviation of 95 pounds. So just so it's clear what we're reading, we actually have information about the cattle population here. So this is the mean of the population. This is the standard deviation of the population. So this is like the big box, the population box. And we already know the mean and we already know the standard deviation. Now we're going to take a random sample out of that population of 100 cows. So we're going to take a sample out, and n is going to be equal to 100. And we're going to find the probability that the sample mean ends up being different kinds of things. So we know the population parameters already. The mean is 1135. The standard deviation is 97. So this is sigma. This is mu. I'm just kind of jotting over to the side. What's the probability that one of your cows weighs between 1,000 and 1,200 pounds? Okay, so we're actually not talking about the mean in this slide. Sorry, this is asking what's the probability that you randomly sample a cow and it weighs between 1,000 and 1,200 pounds. So this is coming from the population of cows, which means that x in this case is going to be normal with mean 1135 and standard deviation 97, because this is coming from the population. So we know this because of this and this. It didn't tell me it's normal. We're just going to assume it's normal. I'm just going to add this here, normal. Okay, so I'm going to find the probability that x is between 1,000 and 1,200. And I'm just going to kind of draw a little picture. So this is 1135. That means 1,000 is going to be over here. And 1,200 is going to be probably closer to there. I'm going to find this shaded region. And this is like a problem I've showed you in a different video. So I've got something normal. I'm going to use the normal CDF command, with my left bound being 100, my right bound being 1,200. Sorry, that's 1,000, 1,200. My mean is 1135, and my standard deviation is 97. I haven't done anything about X bar just yet. I'm using this to show you how we'd find normal probabilities, and I'm going to show you how this applies to X bar on the next slide. There's a very important distinction that I'll show you in these two questions. I'm doing this the same way I did on the video about how to do this in the TI 83, 84. So there's my lower bound, upper bound. I got those from my picture. See, left side, right side. My mean is 1135, and my standard deviation is 97. The probability that I randomly sample a cow, and I get 0.6666. It's not unlucky because there's 4 sixes. So 0.6666. And I don't think it rounds to that. So that's the probability that I randomly sample a cow from this population of bulls, and I get one that's weight is between 1,000 and 1,200 pounds. Okay, so notice, like I said, I haven't done anything with the sample mean yet. This is asking me the probability that one cow weighs this. So this is talking about exactly one cow, which is why I use the population parameters to do this. So one cow. Okay, let's compare that to this next question. So I'm taking a sample of 100 cows. What's the probability, look at all these typos, is the probability that the mean of your sample is between 1,000 and 1,200. So do you see the difference between this question and the one before? This is asking what's the chance the mean is between these two numbers. This is asking what's the chance that one of your cows is between these two things. These are two different questions because the cows follow this distribution. The mean follows a different distribution. The mean follows the distribution. I'll write it up here again. The mean is going to be normal with mean equal to 1135. Let me put the formula up here first. With mean equal to mu and standard deviation equal to sigma over square root of n. So the difference between the last question and this question is the last question I'm using mu and sigma because I'm just sampling one cow, so I'm using this population stuff, and I know it's normal because I scribbled that in there. And this one I'm asking about the sample mean, which means I've got to use this scheme now. So my mean for the sample mean is going to be mu. My standard deviation is going to be sigma over square root of n. So there's my sigma, there's my mu, there's my n. So I'm taking a random sample of 100 cows. So let me show you kind of what this looks like then. My mean is going to be 1135, and I'm looking for the probability. This is the distribution of x bar. And I'm looking for x bar being 1,000 and 1,200. Well, this is x, when we're talking about x bar now. This was the distribution of x. Jot it down over here. Which you're going to say, yeah, they look the same. Yeah, they look the same, but they have different standard deviations. This is going to be different than sigma. It's going to be smaller. Okay. Let me go ahead and find out what sigma is. So x bar is going to be normal with mean 1135 and standard deviation 97 over the square root of 100. This is 97 over 10, or 9.7. So this means that mu x is equal to 1135. So that's that thing. Sigma x bar is going to be 97 over 10, or 9.7. So I'm going to use this mean and this standard deviation to find my probabilities, and then I can do this problem. So the probability that 1,000 is between, x bar is between 1,000 and 1,200 is going to be normal CDF with my left bound is 1,000, my right bound is 1,200, my mean is 1135, and my standard deviation is 9.7. Okay, do you see how this is different than doing this last problem? The last problem, I had the same left bound, same right bound, same mean, but my standard deviation was 97. Using this formula for the sample mean, the distribution of the sample mean, I had to divide this by square root of 100. My standard deviation is different. So if you think my probability is going to be exactly the same as the last question, you're wrong, because this is a different standard deviation. Let me do this real quick on my calculator. I'm going to do normal CDF, and I'll do 1,000 to 1,200. My mean is that. My standard deviation is going to be 9.7. That's a 1. And I get 1. Oh, that's really big. All right, that's not terribly interesting, but I got 1. In other words, my standard deviation is so small, let me do that, 1.00, that this is probably a better way to draw my picture. This is not a very interesting question. My standard deviation is so small that when I draw 1,000 on here and 1,200, they're like way out here. The 1,000 is going to be like way over here. They're like way over here, which means like the area between them is basically basically everything. And I didn't really know that until I did the math, but I just did the math. And the chance that I get something between 1,000 and 1,200 is basically 1, or almost exactly 1. And I guess that's not too surprising, because I know my population mean, and to get something way like this, to get something like within 100 pounds of my population mean on either side is, I guess, pretty certain when I take a sample, because I know the population is normal. Anyway, the point of this example is to show you, like, this is how you find these probabilities. You use the same mean, so this is my mu sub x bar, but your sigma sub x bar is the sigma over the square root of n. And then you can use normal CDF to do things with it. All right, let's do another one. I don't know if these are going to be very interesting because I just kept a lot of these same numbers and changed this word to mean. So it's probably, we're probably going to get some not so interesting answers like 1 or 0 since our standard deviation is so small. Our sigma x is equal to 9.7, and I've got stuff that's like so much bigger than 1135. So maybe I'll change this. Let me change this to like, can I change this to, how about I change this to 1170? Let me change that. Okay, so what's the chance that your mean is greater than 1170? So this is my mean. So the 1170 might go right there. Or it might still be up here. It might still be really big. But I know that my mu sub x bar is equal to 11.1135. That's my sigma sub x bar. I'm looking for this sliver, the chance that I'm greater than 1170. It should be a 0. And I'll do this, I'll use the normal CDF to find this. So see, I'm finding this shaded region. My left bound is going to be 1170. My right bound is going to be some big number. Left bound's 1170. Right bound's going to be some big positive number. Another 9 just for good measure. 1135 is my mean, and 9.7 is my standard deviation. I can do that on my calculator. So normal CDF, 1170 all the way up to, I think I'm doing 7 nines this time. 1135, 9.7, paste. And I get something really small, but not too small. So this just means times 10 to the negative 4. So imagine moving this to the left 4, and that's the number. So I actually get the number 0.0001, but rounded up 0.0002. Let me kind of show you what I mean when I say that. So this is 1.54 times 10 to the negative 4, but I'm going to write that not in scientific notation. So this means move the decimal to the left 4, and I get 0.0002 because that goes up to 2, not 1. So this is my probability. So this is a really tiny sliver. The chance I get a sample mean that's greater than 1170 is 0.0002. There's almost no chance. And that's why I shrunk this number, because if we had done 1300, we would have gotten something like 0. A really small thing. So the point is, when you're finding the probability that the mean of your sample is one thing or another, this is x bar, you've got to use this standard deviation and this mean, which is the population mean. Okay, so that's why I did C this way. That's why I did problem B the same way, using this standard deviation, this mean. Problem A, I did it because it wasn't asking about the mean, it was asking about one of the cows. So you've got to distinguish now between whether it's asking you about one thing or whether it's asking you about the mean of the sample. Because if it's asking about one thing, just use the regular standard deviation. If it's asking about another, use this one, that divided by the square root of n. Okay, I'm not going to do this one because this works the same, and this number's probably not terribly interesting. So I'm going to skip this. This works the same. You're going to do a less than. I want to show you a percentile one. So we're going to find the 90th percentile of the sample mean. We know that x bar is normal with the mean 1135 and the standard deviation 9.7. That's this divided by the square root of 10. So I want to find the 90th percentile, 1135. So this would be maybe right here. This is P90. And the stuff to the left of it's going to be 90%. The stuff to the right is going to be 10%. And I'm going to use, since I'm doing the percentiles, I want to find the number on the number line, which is the inverse, using the inverse norm function. Inverse norm gives me what's on the number line. It asks for the mean, the standard deviation, and the area to the left of this thing. So the area to the left of this thing is 0.9. Those are the three numbers I give this function, and I'll get my answer. So I'm going to do inverse norm. 0.9, 1135, and 9.7. And I get 1147.43. So here we go, 1147.43. Maybe we would round that to something different, but that's the idea. So the point here then is when I'm looking for a percentile for the sample mean, I'm still dealing with something normal. And I would treat this just like any other normal problem. But what you got to be careful of is you got to make sure you get your mean and your standard deviation right. So my mu sub x bar is that. My sigma sub x bar is that. And once I know what this is, I do this just like any other normal problem. I'm going to find the percentiles the exact same way using the inverse norm, the area to the left, the mean, and the standard deviation. And so that's how I would answer that. So the point here of this section, and the reason the central limit theorem is so important, is we can talk about the distribution of the sample mean. We can find probabilities with the sample mean. So like we can find that, or we could find that. This one I skipped, I'm not going to do, but it would be like the probability that x bar is less than 1,000. You can find that the same way. And then you can also find percentiles using the inverse norm function. You treat it just like a normal problem, but you've got to fix the standard deviation before you actually do it. So it's really, really kind of handy because the math is real familiar. And that's how you do problems asking about probabilities and sample means and such.